Hi everyone, welcome back to my video on control systems. In this video, I'm going to explain about the stability margins in the frequency domain analysis. We'll be explaining on how do we derive the gain margin and phase margin from the two common plots that we'll be using in frequency domain analysis, which are the Bode plot as well as the Nyquist plot. The stability margins, namely the gain margin and phase margins, are derived from the concept that we use extensively from the root locus. Imagine a root locus of such. Recall in the past that the root locus spells all the root location of the closed loop poles of the system, where S is equal to the real part sigma plus j omega, the imaginary parts. And if you look at the stability margins, basically we say that the stability margin is defined as the point here, which is located on exactly at the imaginary axis, and any points lie beyond this, which means that it is on the right hand side of the S-plane, the system will be unstable. Hence, when we talk about the stability margin, we are looking at the point S, which is equals to 0 plus j omega. The root locus is all the closed loop poles of the system, which derive from 1 plus g h s equals to 0. By setting the real part equals to 0, we will then have 1 plus g h j omega equals to 0. At the boundary of the stability, which means the stability margin, we will have g h j omega equals to minus 1. That will implies that the magnitude of g h j omega will be equals to 1, and the phase angle or the argument of g h j omega will be equals to negative 180. Or you may use the positive, basically it's the same, but the normal way that we express will be negative 180. Under this provision, let's look at the Bode plot and also the Nyquist on how do we actually get the stability margin based on the angle, which is negative 180, and also the magnitude, which is equals to 1. Let's look at the Bode plot. Okay, we give a typical examples on how the Bode plot will look like in these forms. Okay, let's look at these two plots. On the left, we have a Bode plot of the system, whereby we have the gain that cross at 0 dB here, 0 dB, which means that the magnitude is 1. And if you follow the previous definition of our stability margin, when the gain is equals to 1, which means 0 dB, then the difference between this angle and the line negative 180 will form our phase margin. And we look at on the right, when the phase is equals to negative 180, hence the distance between 0 dB or the magnitude is equals to 1 in a normal scale, hence the difference here will form our gain margin. So this is how we determine the stability margin in the Bode plot for the gain margin and phase margin. Next, we move on to the Nyquist. We consider a typical example of the Nyquist plot as follows. Okay, now we have all the information as required. We back to the same definition where the magnitude is equals to 1, which means this line. Basically, we are actually focusing on this line as highlighted over here. So this line will actually forms our boundary of the stability. We will be observing this point where it crosses at the minus 1 point. The distance from here to here will form the 1 over gain margin. And if you look at the angle, basically we are trying to find this angle. From here to here will form our phase margin. This is how we actually determine the gain margin and phase margin from the Nyquist plot. To demonstrate an exact example of this, we will be using the MATLAB. we'll be defining a transfer function g, where the transfer function is equal to 10 over s cubed plus 4s squared plus 5s plus 1 in MATLAB. And now I'll be creating a body plot, and I'm going to set the background to white. To view all the stability margin in the body plot, I can right click, characteristics, and choose all stability margins. And you'll find here there are two dots that has been highlighted, which is our gain margin and phase margin. So let's look at the gain margin over here. So the gain margin here shows that it's 5.58 dB, and our phase margin is showing as a 23 degree. We'll be looking at how do we determine this 5.58 dB over here. First thing is that we have to identify the frequencies when the phase is equal to -180, and then we look upwards and we measure the distance between here and 0 dB. So the distance from here to here will be our gain margin, but take note there's a sign difference that you have to take note in here, which means that if these dots over here is below 0 dB, then we say that this is a positive gain margin. But if it's the reverse, that this dot is above the 0 dB, then you will result in negative gain margin. A negative gain margin, which means that the system is unstable. We now look at the phase margin. How this phase margin is being calculated over here is we have to check the frequency when the gain is equal to 0 dB, which is somewhere here. Then you have to project downwards like this. And the distance between this point and -180 will be our phase margin. When the phase is above -180, it will result into positive phase margin, and if it's downwards, then it will result us into the negative phase margin. Next, we use the Nyquist command to determine the Nyquist plot. Similarly, we can right-click characteristics or stability margins to determine the gain margin and phase margin. We look at this point. This will be our gain margin, and this dot will show us the phase margin. The phase margin and the gain margin over here, basically it will agree with the one that we obtained from the body plot. So how do we actually obtain these two? Again, what you need to do over here to find out the gain margin is to measure the distance between here to here, and that will be our 1 over gain margin. And to transform it into a dB, basically you just need to do a very simple job, which is you just do 20 log base of that, the gain margin, then you can get the 5.58. So what needs to be done to get the 5.58 is you just have to locate this point, which is somewhere around here. I will try my best to put it as close as possible. Okay, somewhere around here. And the one that will be interested will be this 0.526. So how you get from here to 5.58 is basically it is just 20 log 1 over 0.526, and you'll be able to get 5.58. Next, we move on to determine this 23. Similarly, what we need to do is to locate the points here. What we need to do is just to check on these two values, 0.915 and 0.385, and the phase margin is defined as the angle between these two lines. Hence, it will be inverse tangent of 0.385, the imaginary part, divided by the real part, 0.915. This you should get approximately equals to 28 degrees as shown in here. Okay, in this video I have shown how do we get the stability margins, which are the gain margin and phase margin, from both the body plot and also the Nyquist diagram. Thank you very much for watching. Bye.